Assalamualaikum and hi. My name is Muhammad Adam Haris bin Muhammad Zaidi. My matric number is 230380.
Salam Sejahtera Doctor. My name is Lim Ye Shen. My matrix number is 230847.
Hello and good day. My name is Aman Azran bin Ahmed Nazri and my matric number is 227356.
Hello, Assalamualaikum. My name is Izzuddin. My name is Muhammad Izzuddin bin Muhammad Ustaz and my matrix number is 228798.
So today we are going to present our CND 3200 project for this semester 3. So these are the list of our team members. So we have Amar, Izzuddin, Lim and me, Adam, for the group 1. So what are we doing? On this project, we are basically trying to study network, mainly about everything that is around us. We use a number of tools to scan network to show what data can be acquired. In this presentation, we will talk about the tools, what we do with them, and lastly, what steps we can take to ensure our safety in the digital realm. By the end of the presentation, you will know the uses of each tool and how to use them. Now, let's move on to the introduction to tool. In this project, we utilize four specific tools to analyze and monitor network performance. First, we have ping plotter. This tool provides a powerful combination of ping, visualization, and time tracking service. We use it to observe network performance over time, which allows us to detect critical issues like latency spikes, jitter, and packet loss. It essentially helps us pinpoint whether a connection problem lies near the user or within the internet service provider's network. Next is Open Visual Traceroute, or OVTR. This tool takes data packets and display the route they can across the network. It shows us every hop, the IP address, and even the approximate geographical location on a visual map. We use this to identify routing and route stability, which complements the performance data we get from ping plotter. Our third tool is the Domain Name System Checker, or simply DNS Checker. We use this to verify how a domain name resolves across the internet by checking the DNS records that translate names into IP addresses. This is crucial for monitoring DNS propagation and detecting issues like misconfigured records or outdated servers. We choose this specific tool because of its user-friendly web interface and its ability to check multiple DNS record types simultaneously. Finally, we have TCP View. This application displays all active TCP and UDP connection on a computer in real time. It gives us a granular look at remote addresses, ports, and process name. We prefer TCP View because of its dynamic updates and filtering features, which make monitoring active connection much easier and clearer.
I'm going to present about the results of our task A, which is connection to Princeton's official website using College Chancellor's Wi-Fi. Using ping plotter at 9 to 10 a.m., the result shows that packet loss is at 100% at hop 9, and there's no DMS name at hop 8 and 9, and the latency is 11 milliseconds. The total hop is 12. At 3 to 4 p.m., the packet loss shows that it's 100% at hop 9, no DMS name at hop 7, 8, and 9. The latency is 17 milliseconds and the total hop is 12. This shows that this result shows that the increase in latency in 3 to 4 p.m., which shows that the connection is more busy during 3 to 4 p.m. Maybe due to more people are using it. Let me continue. For 11 p.m. to 12 a.m., the packet loss in pink plotter shows that there's 50% packet loss at hop 5, 100% loss at hop 8 and 9, packet loss 25% at hop 12. There's no DMS name at hop 8 and 9. The latency is 16 milliseconds and the total hop is 12. So which means that the connection might not be as busy as 3 to 4 p.m. but it's still busy due to modern lifestyle. Now I will present about the results of connection to Princeton's official website from College Chancellor, the College Chancellor's Wi-Fi using Open Visual Trace Route. So during 9 to 10 a.m., the end-to-end road trip time is approximately 0 milliseconds, where we're using latency of the last hop to approximate. There's no packet loss, the response time is slightly slower after hop 6, and the total hop is 12, which match our results from the pink plotter. Let me continue for the time frame 3 p.m. to 4 p.m. The end-to-end round trip time, which we're using latency of last hop to approximate, is approximately 0 milliseconds. There's no packet loss, but the response time is slightly slower after hop 9. The total hop is 12. To continue, the results for Open Visual Trace Route at time slot 11 p.m. to 12 a.m. is the end-to-end round trip time, where we're using the same method, latency of last hop to approximate, is approximate 0 milliseconds. There's no packet loss, but the response is slightly slower after hop 6. The total hop is 12. I will continue to present the result of connecting to Princeton's official website using College Chancellor's Wi-Fi via DNS checker. So from the time slot 9 to 10 a.m., there's two type A address result, which shares the same time to live, which is 300, but both of them uses different address, which is 104, 18, 4 and 101. Another one is 104, 18, 5 and 101. And the canonical name shows one result which using the time to live of 3208. The canonical name is www.princeton.edu.cloudflare.net.edu. Okay. www.princeton.edu.cdn.cloudflare.net/net. Okay. In the time slot of 3 to 4 p.m., there's two type address result too, which also shares the time to live of 300. And one of the address is 104, 18, 5 and 101. Another one is 104, 18, 4 and 101. And the canonical name, which is for the alias domain, is have a time to live of 3347, and also shares the canonical name of www.princeton.edu.cdn.cloudflare/net. Okay. Let me continue for the time slot of 11 p.m. to 12 a.m. The type A, which is address, shows two results which share the same time to live, which is 300. And the address is 104, 18, 5, 101. And another is 104, 18, 4 and 101. The result for Princeton EDU canonical name, which is the time to live is 3347, and the canonical name is www.princeton.edu.cdn.cloudflare.net/net. Let me present the results of TCP view from connecting the official website of Princeton from College Chancellor Wi-Fi. So we filter the result using 443, which is a showing of HTTPS, and we locate the actual Google search the using the IP address we found in DNS checker, and so we got the result from 9 to 10 a.m., which is the endpoint is 821, established is 40, listening is 29, time waited is 27, and close wait is 2. For the time slot 3 to 4 p.m., the endpoint is 833, established is 35, listening is 29, time waited is 2, and close wait is 5. Lastly, the result of TCP view at the time slot 11 p.m. to 12 a.m. is the endpoint is 783, established is 53, listening is 29, time waited is 19, and close wait is 5.
So today I'm going to talk about the analysis from Suburban using Unified in access to the fsktm.upm.edu.my website. Alright. So first thing first, I check the speed using the ping plotter tools for at time 9 to 10 a.m. And from the result, I get they have a packet loss at hop 6 and 7. From that, I get the no DNS name at hop 6 and 7 because they lost totally 100% at that two hops. The average latency is 37 millims and the total hop is 20 at this time. And next, I do the analysis from 3 to 4 p.m. At this time, I have a packet loss of 0.4% at hop 4 and packet loss totally 100% at hop 6 and 7. At this time, there are no DNS name at hop 6 and 7 because when they have no DNS name, they actually lost a total 100%. And the total latency happen here is 87 ms. And the total hop I get is 17. Move to the next. I do the same for the analysis using Unify at different time. And it actually 11 p.m. to 12 a.m. Here they have a lot of packet loss that happen. For the first, I have packet loss 99.4% at hop 4. Packet loss 50.9% at hop 5. Packet loss 91.2% at hop 6, 0.5% at hop 10, and 0.9% at hop 11. And as I mentioned, uh, they have a total packet loss at hop 8 and 9. And the latency I get is quite high, and it's actually 232 ms. And this here I get a little bit total hop, and it is 12. Move to the next. I use the tool called Visual Road, and from here I get analysis from the tool that where the hop responding on average is actually and for, I'm test this using this tool at 9 to 10 a.m. and the hop responding on average is 11 ms to 15 ms. They have no packet loss, and the response is slightly slower after hop 7, and the total hop I get is 17. Next, I use this tool at 3 to 4 p.m. and the hop responding on average is 10 to 15 ms. There are no packet loss, and the response slightly slower after hop 10, and the total hop is 17. And I also do the same for this tool. I do at 11 p.m. to 12 a.m. using Unify 2. The hop responding on average is 0 ms to 235 ms. There are no packet loss, and the response slightly slower after hop 10. And the total hop for this time is 10, and it's actually is and they have a higher ms after hop 12. And then I'm using the DNS checker to show whether this IP address I use in my project. So for the analysis from 9 to 10 a.m. and I'm used to type. I find the result by find the TTL number and CNAME number, and I get a the A number is A300 and CNAME is 300. And I'm do the same for the DNS checker at 3 to 4 p.m. And this I get the same number for the A38, which is 300, but the CNAME is slightly is lower and is 139. Analysis from suburb 6 to at 11 p.m. to 12 a.m. for the NS checker. I get 300 for A and 300 for CNAME. And next, I use tool like TCP view. From this from this tool, I get the information like the endpoint, established listening, time weighted, and close weight. From 9 to 10 a.m. From 9 to 10 a.m., I get the endpoint number is 219. Established 111. Listening 14. Time weighted 119. And close weight is 0. And from the analysis from Suburbanum using Unified to FSKTM at 3 to 4 p.m. For the endpoint, I get 355. Established 33. Listening 32. Time weighted 119 and close weight is 1. And next, I do the same for the TCP view, but at 11 p.m. to 12 a.m. For the endpoint, I get a little higher for 687. Established 1, 13. Listening 32. Time weighted 246. Close weight 98. From all the from all the analysis that I get from these tools that I have used, I can get that when I do the research at 9 a.m. to 10 a.m. and 3 p.m. to 4 p.m., I get the average MS and it is quite fast. But when I do the analysis at 7 p.m. and 12 a.m., all the speed becomes slower. That is from the analysis that I get from the tool that I have used. Thank you.
So I will be explain about analysis from suburb 6 using Celcom to fsktm.upm.edu.my. So this slide is about imploted. First, when we observe from 9 a.m. to 10 a.m., we can see that packet loss 100% at hop 6, 9, and 10, loss 0.4% at hop 8 and 12, no DNS name at hop 6, 9, and 10. Latency is 537 ms, and the total hop is 20. So, what does it mean? During morning hours, the Celcom mobile network shows server instability. High packet loss means that many packets never reach their destination, causing slow or failed connections. The missing DNS name indicate backbone or mobile carrier routers that do not respond to ICMP requests. Overall, the network performance is poor. Next, we observe from 3 p.m. to 4 p.m. we can see that packet loss 100% at hop 2, 3, 4, 7, 10, and 11. Some that lost at 90% at hop 8. No DNS name at hop 2, 3, 4, 7, 10, and 11. Latency is 517 ms and the total hop is 21. So, in the afternoon, network congestion increases due to peak mobile usage. Although the number of hops is lower, latency becomes worse. This shows that fewer hops does not always mean better performance. The high packet loss suggests heavy congestion in Selkoff mobile core network. Move on, we observe from 11 p.m. to 12 a.m. So packet loss 1.4% at hop 1, packet loss 64.6% at hop 2 and 3, lower than its name at hop 7 and 8, latency 569 ms, and the total hop is 16. What we observe at night, network congestion is reduced. Cellcom's mobile network becomes more stable with lower packet loss and better response time. This demonstrates how time of day strongly affect mobile network performance. So, from Sabak Benam using Celcom, Pink plotter clearly shows that mobile data connection are highly affected by congestion, especially during daytime. Nighttime usage provides the best performance for accessing FSKTM. Next, I will explain about the visual route analysis from Sabak Benam using Celcom to FSKTM website. So at 9 a.m. to 10 a.m., we can see that hops responding on average is from 11 ms to 15 ms. No packet is lost. Response slightly slower after hop 7. The total hop is 17. So, visual route shows a stable logical path with consistent hop responses. However, it does not reveal packet loss like pink plotter. This means the loss exists, but quality issues still occur underneath. Moving on at 3 to 4 p.m. Hops responding on average 10 ms to 15 ms. No packet is lost. Response slightly slower after hop 10 and the total hop is 17. Although the route appears shorter, response time fluctuates significantly. This confirms congestion within Selkov's internal routing during peak hours. Furthermore, at 11 p.m. to 10 a.m., hops responding on average 0 ms to 235 ms. No packet loss. Respond slightly slower after hop 5. The total hop is 10. Similar to pink plotter results, visual route confirms that late night connections are more stable due to the reduced mobile traffic. So the conclusion, visual route confirms that Celcom provides a valid routing path to FSKTL website, but performance degradation during peak hours occurs inside the mobile network, not due to the routing failure. Next, I will explain about the DNS checker analysis from Sabak Menam using Celcom to FSKTM website. So as we can see here at 9 to 10 a.m., the TTL type A is 300 and for type C name is 300. Moving on, at 3 to 4 p.m., the type A TTL is 300 and the type C name is 139. from 11 p.m. to 12 a.m. The type A TTL is 300 and the type C name is 300. So, DNS resolution for FSKTL website is stable and consistent regardless of type or network. This confirms that performance issues are not caused by DNS problems but by the network transmission issues. So, DNS is functioning correctly. The delays and packet loss observed earlier are caused by network congestion, not same resolution failures. Lastly, I will explain about the TCP view analysis from Sabak Bernam using Cellcom to FSKTL website. So from 9 to 10 a.m., the endpoint is 111, established at 9, listening at 24, time waited is 31, and close wait is 0. So, fewer established connection indicate difficulty maintaining stable sessions due to packet loss and high latency. Moving on, at 3 to 4 p.m., the endpoint is 316, established at 31, listening at 32, the waited is 81, and the close wait is 13. So, increased time wait state suggests frequent connection drop and retires, consistent with unstable mobile network condition. And lastly, at 11 p.m. to 12 a.m., the endpoint is 310, established at 31, listening 32, the waited is 73, and the close wait is 4. So, most stable connections are maintained at night, confirming improved network quality. So, the conclusion is TCP view that's unstable mobile connectivity causes frequent connection retires during peak hours, while off-peak hours allow more stable TCP session. From Sabak Brunei using Celcom, our analysis shows that mobile data networks are highly sensitive to time-based congestion. DNS resolution remains stable, routing path exists, but high packet loss and latency during peak hours significantly degrade performance. Nighttime users provide the most reliable connection to FSKTL website.
To wrap up our findings, I like to share the summary of our analysis. From the discussion, we focus on 4 key areas. First, latency assessment. Through our ping test to Google DNS, we demonstrate how network topology can directly influence packet loss. Second, discovery of nearby devices. By using DNS filtering, we reveal the presence of local device. This shows us just how easily network broadcasts can leak user information, especially in public Wi-Fi environment. Third, network topology mapping. Using traceroute via both CLI and the ping plotter GUI, we provide clearer visualization of path characteristics such as delivery accuracy and jitter. And finally, wireless signal analysis. Our TCP view measurement help us quantify how physical distance and environmental factors actually degrade Wi-Fi signal strength. Based on the vulnerabilities we discovered, here are our recommendations for future network analysis to ensure better safety in the digital realm. We strongly recommend using website with HTTPS and internal application. This prevents credential leakage during packet capture. Number 2, regular vulnerability scanning. You should schedule periodic scans using tools like Nmap. This helps identify open ports and outdated service that could be exploited. 3. Use visualization tools. Instead of relying solely on text data, use GUI-based tools like PingPlotter or NetSpot. This monitoring dashboard significantly simplify the interpretation of complex data like latency and jitter. Number 4, isolate sensitive traffic. Finally, use LANs or VPNs for critical systems. This limits broadcast domains and reduce the exposure of Discovery Protocol to the wider network. So this is our reference for this project. So thank you very much. That's all from me. That's all from us.